It's a ethical hacking disclaimer. This video serves educational purpose only. It does not promote illegal activities. Viewers are responsible for any misuse of information related to ethical hacking, cybersecurity awareness. Welcome back to Black World YouTube channel. Today we dive deep into FFUF Fuzz Faster U Fool. This is not just another fuzzer. FF is a purpose-built, high-performance web fuzzer written in Go. It's designed for security professionals, bug bounty hunters, and developers who need to discover hidden content, parameters, or virtual hosts. Unlike older tools, FF gives you full control over matches, filters, concurrency, and even raw request fuzzing. By the end of this session, you will understand every flag from the help menu and you'll be able to craft precise, intelligent fuzzing campaigns. We'll cover HTTP options, matches, filters, input modes, output formats, and even advanced features like auto-calibration and recursion. Let's start with the foundation. What is web fuzzing? Web fuzzing is the art of sending many HTTP requests to a target, each with a slightly different input, and observing the responses for anomalies. We mark the place to fuzz with the fuzz keyword. Then FF replaces fuzz with each line from a word list. Think of it as trying thousands of keys on a lock. We look for status codes, response sizes, words, lines, timing, or even regex patterns that indicate something interesting. For example, fuzzing/fuzz might find hidden directories like /admin or /backup. Fuzzing a parameter like id equals $fuzz might reveal SQL injection. Fuzzing is a brute force method, but with smart filters, it becomes a precision tool. FF makes this faster, easier, and more reliable than any alternative. Let's see the simplest command. The most basic FF command is FFOW wordlist.txt u https://example.com/fuzz. Here, W points to your word list A text file with one payload per line. The U flag is the target URL, and you put the keyword fuzz exactly where you want the payloads inserted. By default, FFU uses the get method. It also automatically matches HTTP status codes in the ranges 200, 299, 301, 302, 307, 401, 403, 405, 500. That means it hides boring 404s, but it still shows 403 forbidden, which might mean the path exists but you can't access it. You'll see a live progress bar, and each match is printed to the terminal. This simple command can discover thousands of hidden paths in seconds, but real fuzzing requires control. Let's talk about speed. One of the F's in FF stands for faster. By default, FF uses 40 concurrent threads. D40, that means up to 40 requests are sent simultaneously, dramatically reducing total runtime. For example, testing a 10,000 word list with one thread might take 5 minutes, assuming 30 ms per request with 40 threads. It could finish in under 10 seconds. However, concurrency has risks. Too many threads can overwhelm a server, trigger rate limiting, or get your IP banned. For local testing or CTF, 4100 is fine. For live websites, start with T10 and increase slowly. Each thread is independent delays PR per thread, not global. Also note, concurrency does not mean parallelism in the CPU sense. It's asynchronous I/O. FF uses Go's coroutines, which are lightweight and efficient. Always balance speed with stealth. By default, FFUF sends GET requests, but many web applications expect other methods. Use X to change the method, for example, XPost or XPut. You can also fuzz the method itself by putting the fuzz keyword inside X example. Xfuzz with a word list containing get, post, put, patch, delete options. This tests for insecure method configurations. More commonly, you'll use expose to fuzz form parameters or API endpoints, combined with data for post bodies. Remember that different methods might trigger different logic. A delete on an API might be restricted, but a get might leak info. Also, some servers respond with 405 method not allowed, which itself is useful information. FF handles all HTTP methods defined in RFC 7231. You can even use custom methods like propfind for web fuzzing. Methods are case sensitive, use uppercase. Now let's look at headers. Web applications rely heavily on HTTP headers for routing, authentication, and bot detection. With H, you can add any header. Even better, you can fuzz any header by including the fuzz keyword. For example, H host fuzzes virtual hosts. You might discover admin.internal.example.com that resolves to the same IP. Another example, H user agent fuzzes tests if the server behaves differently for different browsers or bots. For cookies, use B session equals sign fuzz to fuzz session tokens or B user equals sign fuzz to test cookie injection. Multiple HF flags are allowed. You can also combine headers with cookies. Important. FFUF auto handles cookie formatting. Just put the string as you would in a curl command. Headers are case insensitive per HTTP spec, but FFUF preserves your casing. Fuzzing headers can uncover host header injection, X forwarded for bypasses, and more always include realistic headers like accept and connection to avoid obvious bot detection. Modern APIs send data in the request body, not the URL. Use D to specify post data. You can place the fuzz keyword anywhere inside that data. Example D, username equals sign admin and password equals sign fuzzes for a login brute force. For JSON APIs, first set the correct content, type header with H content, type application/JSON. Then provide JSON data, the username, fuzz, password, FFUF. Will replace fuzz with each word list entry and send it as a post request. You can also fuzz multiple fields by using multiple keywords. For example, W users, user, W pass, and D user, user pass. The data is sent exactly as given, no automatic URL encoding unless you use ENC. Be careful with special characters. If your payload contains quotes or backslashes, escape them properly for your shell. For large post bodies, consider using request with a raw file. Post fuzzing is essential for testing registration forms, search boxes, and API endpoints. By default, FFUF does not follow redirects. It reports the initial response, for example, a 301 or 302 without fetching the destination. This is often what you want because the redirect location itself may contain clues like a session ID. However, sometimes the final destination after a redirect holds the real content. Enable R to make FF follow redirects transparently. It will then show you the status code and size of the final response. This is crucial when testing login forms that redirect to a dashboard upon success, or when certain directories automatically redirect. For example, /admin to /admin/login. Without R, you might see only a 302 and mistakenly ignore it. With R, you see the 200 of the dashboard. But be aware, following redirects increases request count and time. FFUF specs redirect chains up to a limit, usually 10. It also passes headers and cookies through redirects, unless the domain changes. Use R when you care about the final page, not the redirect itself. Recursion is one of FF's most powerful automation features. With recursion, FFUF will automatically fuzz newly discovered directories again. How? You fuzz/fuzz and find /admin. FF then launches a new job, fuzzing/admin/fuzz. This continues recursively. You control the maximum depth with recursion. Depth default 0 = unlimited. There are two strategies. Default only recurs on responses that are directories, usually 300 seconds with a trailing slash, and greedy recurs on any match. Regardless of status code, greedy can cause massive request explosion. Recursion requires that your URL ends with fuzz. Example: https://sample.com/fuzz/trailing/. Recursion is incredibly useful for mapping an entire website structure. But be careful, a single directory like /assets might have thousands of subdirectories. Always set a depth limit and combine with size filters. Also, recursion respects your matches and filters, so only interesting directories get fuzzed further. Matches and filters are what make FF intelligent. Matches tell FFUF, show me responses that meet these criteria. Filters tell FFUF, hide responses that meet these criteria. You have 6 types each: status code MC/FC, line count ML/FL, regex MR/FR, response size MS/FS, response time MT/FT, and word count MW/FW. By default, matches are on status codes 200, 299, sextillion, 301, quintillion, 302, quadrillion, 307 trillion, 401 billion, 403 million, 405,500, and filters are off. You can combine multiple matches using M mode and OR. For example, MC200 M mode and MS1000 shows only responses that are 200 and larger than 1000 bytes. Similarly, filters combine with F mode. This allows you to cut through noise. For instance, a typical 404 page might be 489 bytes with 8 lines. Set FS 489 and FL8 to hide it. Mastering matches and filters turns a brute force tool into a targeted discovery engine. Always start with broad matches, then iteratively add filters. Status codes are the fastest signal from a web server. The MC flag specifies which status codes to match show. Default is 200, 299, sextillion, 301, quintillion, 302, quadrillion, 307 trillion, 401 billion, 403 million, 405,500. That's a wide range. It shows success, redirects, unauthorized, forbidden method, not allowed, and server errors. Why include 403? Because a 403 often means the directory or file exists, but you lack permission. That's valuable information for later manual testing to override. Use MC 200,204,302 or MC all to show everything. For filtering, use FC 404,403 to hide those. You can also use ranges. FC 400, 499 hides All client errors. Status code fuzzing is very fast because FF can stop reading the response body after the status line use. Ignore body for even more speed. But status codes can be misleading. Some applications return 200 for error pages. That's why you need other matches. Always verify a few matched responses manually. A 200 might be a custom 404 page. Sometimes status codes and sizes aren't enough. You need to peek inside the response body. Use MR match regex to show only responses that contain a certain pattern. Use FR filter regex to hide responses containing a pattern. Example: MR admin vertical bar root vertical bar config finds any response mentioning admin, root or config. FR page not found hides generic 404 pages even if they return 200. Regex in FFUF uses goes regexp syntax here too. It's fast but doesn't support look ahead or back references. Keep pattern simple. Precompile your regex for large word lists. Regex is case sensitive by default. Use I for case insensitive MR. Another powerful use: MR SQL syntax.*MySQL to detect SQL error messages. You can combine regex matching with other matches using MR mode. However, regex is slower than size/line matching because the full response body must be fetched. Use it sparingly on large targets. When it hits, it's often a gold mine. Every HTTP response has a size bytes, number of lines, and number of words. These can be powerful discriminators. Use MS to match size, ML for lines, MW for words, filter versions FSFLW. For example, a standard Apache 404 might be 1995 bytes, 20 lines, 150 words. You can filter it out with FS 1995, but dynamic pages vary. That's why you can specify ranges. FS0 1000 hides small responses, FS 5000 hides only very large ones. Why use line/word counts instead of size? Sometimes size changes due to timestamps, but line count remains stable. For example, a not found page might have exactly 10 lines regardless of the request. Use FL10 to filter it. Word count is useful for JSON responses where the number of tokens changes. Remember that FFUF counts words as sequences separated by whitespace. Combined with status code filters for best results. Always calibrate using a known invalid request first. Response time can reveal hidden behavior. Use empty match time and FT filter time with comparisons 150 etc. Time is measured in milliseconds to the first response byte. Time to first byte TTFB example. MT2000 shows only requests that took longer than 2 seconds. Why would a request be slow? Database queries, file processing, external API calls, or intentional delays caused by blind injection. For instance, a blind SQL injection with wait for delay might cause a 5-second pause. Time filtering catches that. However, network jitter and server load cause false positives. Run multiple passes or combine with other matches. Also note, FF's default timeout is 10 seconds. Timeout: if a request takes longer than that, it's considered an error and not shown unless you adjust. Time filtering works best on stable local environments. For remote targets, use a large range, for example, MT1000, and manually verify. Never rely solely on timing, it's an indicator, not a proof. Auto calibration AC is a brilliant feature that automatically removes false positives. How? FFUF first sends a request to a known invalid path, appending a random string. It analyzes the response status, size, lines, words, and even rejects patterns. Then it builds filters that would hide that exact response. Those filters are then applied to all real fuzzing requests. This means you don't need to manually figure out that 404 pages are 432 bytes with 12 lines. FF does it for you. You can customize the calibration keyword with ACK. Use ACC to add custom strings, useful if the application has multiple error patterns. ACS selects strategies, for example status, length, words, and H enables per host calibration, important when fuzzing multiple virtual hosts. Auto calibration is not perfect. It may overfilter if the invalid response coincidentally matches a valid page. Always run a small test without AC first. For large unknown targets, AC saves hours of manual filter tuning. The W flag specifies your wordlist basic w/path/to/wordlist.txt. You can assign a custom keyword wdrs.txt dr and then use dr in the URL instead of fuzz. This allows multiple word lists with different keywords. The E flag adds extensions, example ePHP, HTML, ASP. For each word from your word list, FF will also try that word with each extension appended. So if your word list has admin, FFF tries admin, admin.php, admin.html, admin.asp. This is perfect for finding backup files or alternative script extensions. Combined with D for the search compatibility mode, which treats /fuzz as directory and automatically adds extensions after /actually. D changes how extensions are appended. See docs. Be careful. Extensions multiply your request count. If you have 10,000 words and 5 extensions, that's 50,000 requests. Use with appropriate rate limiting. Word lists matter. Use curated lists like sec lists or generate your own from crawling. When you use multiple word lists, for example, wusers txt user wpass txt pass, the mode flag decides how they combine sniper. Mode sniper, only one keyword is fuzzed at a time, others stay static. Example, first fuzz user while pass is constant, then fuzz pass while user is constant. Pitchfork, mode pitchfork, takes the first word from each list, then second, then third lists must have the same length, or the shorter one is truncated, useful for pairing usernames and passwords from a pre-matched list. Cluster bomb, mode cluster bomb, generates every combination Cartesian product. This is the default. With 3 usernames and 3 passwords, you get 9 requests. Cluster bomb is powerful but can explode combinatorially. 1000 x 1000 equals 1 million requests. Always estimate before running. The keyword names are case sensitive. You define them after colon in WFFF uses the keyword names to replace in the URL, headers or data. Understanding modes helps you choose the right attack. Static word list files are great, but sometimes you need dynamic generation. Use input cmd to specify a command that outputs word list lines. For example, input cmd seek 1 million inches generates numbers 1 to 1 million. You must also provide input num with the expected total number of lines. FF uses this for progress calculation and to know when to stop incorrect. Input num can cause early termination or infinite loops. Another example, input cmd curl as https://api.example.com/users vertical bar jqr. Name pulling live data from an API. Use input shell to specify a different shell, default/bin/s on Unix, cmd on Windows. Dynamic input is perfect for time-based values, sequential IDs, or data that changes between runs. However, it's slower than file input because the command must run and its output must be read before fuzzing starts. Also, the command runs only once at the beginning. For repeated runs, consider generating a file. This feature turns FFUF into a program fuzzing. When your request is complex, many headers, a specific body format, or unusual line breaks, typing everything on the command line is error-prone. Use request to load a raw HTTP request from a file. The file must be a complete valid HTTP request, like what curl we would show. Place the fuzz keyword anywhere in that file method, path, headers, body. FFUF will replace fuzz with each wordlist entry and send the request. Example FFUF request req.txt w wordlist.txt. You can also set the protocol with request proto default HTTPS. Important, the host header in the raw request will be used. FFUF does not automatically change the destination unless you specify a different URL with U, which overrides. Raw request mode is fantastic for fuzzing HTTP 1 features like transfer, encoding, X forwarded for chains. It also preserves exact spacing and line endings, which can be critical for passing bugs. Always test your raw request with vfuzz to ensure FFUF sends what you expect. Terminal output is ephemeral. For real work, save your results. Use O output file to write the output. Combine with OF to choose format, JSON default EJSON. Extended JSON with more metadata, HTML human readable report, MD markdown table, CSV or ECSV. You can also use of all to generate all formats simultaneously, useful for archival. The R flag prevents creating an output file if no results were matched. Useful in scripts, JSON output is machine readable for further processing with JQ example. FFUF O results.json of JSON, then cat results.json vertical bar JQ. Results input HTML output is great for sharing with non-technical stakeholders. CSV opens in Excel for pivot tables. When using recursion, output files contain all matches from all levels. Be careful with large result sets. A 1 million request fuzz might produce a huge JSON file. You can also output to stdout. Use O for piping to other tools. Always save at least JSON. You'll thank yourself later. Sometimes you want to inspect all traffic in another tool like Burp Suite or Wasp app. Use X to route all requests through an HTTP or SOCKS 5 proxy. Example xHTTP/127.0.1 for burp. For SOCKS 5, xSOCKS 5/127.0.1 This sends every fuzzing request to the proxy, which forwards to the target. However, that's a lot of traffic. Burp might slow down or crash. That's where replay proxy shines. It sends only matched responses, the interesting ones, to a separate proxy, so you can fuzz at full speed, and only the rare matches are replayed to burp for manual testing. The replay proxy can be different from the main proxy. For example, http://127.0.0.18080 main proxy and replay proxy http://127.0.0.18081 replay proxy. This is an advanced workflow used by professional bug bounty hunters. Note: proxy support works with HTTP 1.1. For HTTP 2, proxy support is limited. Also, authentication to proxies is not built in. Use upstream proxy with auth. Fuzzing too fast can trigger rate limiting, WAF bans, or even denial of service. Use rate to set a global maximum request per second. Example: rate 20 equals sign 20 requests per second, spread across threads. FF uses a token bucket algorithm to enforce this. For random delays between requests per thread, use P0.1, 0.5 inches a random pause between 100 and 500 milliseconds. Delay is per thread. If you have 40 threads and P0.5, you might still send 80 requests per second because threads run in parallel. To achieve a true low rate, combine T1P1, 1 request per second. Why use delay instead of rate? Delay mimics human behavior better, reducing WAF detection, but rate is more deterministic. For stealth, use P0.5, 1.5 with T5. Also, don't forget timeout if a server is slow. A low rate won't help if requests pile up. Always test with a small word list first. Respect robots.txt and terms of service. Getting banned from an IP is not just annoying, it kills your test. Network issues and server blocks happen. Timeout default 10 seconds sets how long FF waits for a response before aborting that request. Increase for slow targets. Set stop on spurious errors if any network error, connection refused, reset, etc. occurs. FF stops. Useful in stable environments to avoid continuing after a network failure. SF stops when more than 95% of responses are 403 forbidden, a clear sign you've been blocked by a WAF or IP ban. Says stops on all errors implies C and SF and also stops on empty responses, pass errors, etc. For total runtime limits, max time stops the entire process after n seconds. Max time job stops each job, for example each recursion level after n seconds. These are safety nets for long fuzzing sessions. Without them, a stuck recursion could run forever. Example, max time 3600 stops after 1 hour. Always set max time for unattended fuzzing. Also, note that timeouts and errors are logged to debug log. When results don't match your expectations, enable vverbose. It prints the full URL, the redirect location if any, and the response status for each match. This helps you understand what FF actually sent and received. For deeper debugging, use debuglogfile.txt. This writes a detailed log of every internal event. When a request starts, when a response is received, which matches/filters triggered, and any errors. The debug log is invaluable for reporting bugs or understanding why a response was filtered incorrectly. Warning: the debug log can become huge gigabytes on large fuzzing runs. Use it only on small tests or with max time. Verbose mode does not slow down FF significantly. It only prints more to the terminal, which might cause lag if you have thousands of matches. In those cases, redirect stdout to a file or use oprotip. Run a small test with v and o/dev/null to verify your command before a big run. Debug logs also show timing per request. FF features an interactive console that you can activate by pressing I while fuzzing. Once in interactive mode, you can type commands to dynamically add or remove filters and matches without restarting. For example, you see many false positives of size 1024 bytes type FS1024 to filter them out. Type clear to reset filters. This is incredibly powerful for live exploration. You start with minimal filters, then tighten them as you observe patterns. You can also adjust concurrency, tint 50, change rate limit, or save current results. The console has tab completion and help. However, in automated scripts, CI/CD cron jobs, the interactive console will hang waiting for input. Use non-interactive to disable it entirely. Without this flag, FF still runs normally, but the console is available. For headless environments, always add non-interactive also. Note that some output formats like JSON conflict with interactive output. The console may corrupt JSON lines. Every matched response in FFO and only matched responses is assigned a unique identifier called FFUF. You can later rerun that exact payload using search FFUF. Why would you need this? Imagine you ran a huge fuzzing session and found one particularly interesting response. You want to examine it again with different options. For example, verbose replay proxy. Instead of trying to reconstruct the exact URL and payload, you simply run ff search a1b2c3 w original underscore wordlist.txt usame underscore url underscore fuzz. FF will send only that one request. The hash is printed in the output when you use V or in JSON results. It's based on the payload value, not the position, so it's stable across runs as long as the word list doesn't change. This feature is also useful for debugging. If a match looks suspicious, you can search and replay it with debug log to see exactly what happened. Note that search requires the same word list and URL structure. Server name indication SNI tells a TLS server which hostname you're trying to reach. Most of the time, FFU extracts length SNI from the URL's hostname. But sometimes you need to override it, for example, when testing a reverse proxy that expects a different SNI than the URL host. Use SNI to set a custom SNI. Note fuzz keyword is not supported for SNI. HTTP2 is becoming the standard. Use HTTP2 to enable HTTP2 protocol. HTTP2 can be faster because it multiplexes multiple requests over a single connection, reducing TCP handshake overhead. However, some servers behave differently under HTTP1. 1 versus HTTP2. For example, WAF rules might only inspect HTTP1. 1. FFUF supports HTTP2, but with limitations. Not all matches work identically. For example, trailing headers and proxy support is limited. Also, HTTP2 uses hatchback header compression. FFUF handles it transparently. For most fuzzing, HTTP1 is sufficient and more compatible. By default, FFO URL encodes special characters in the fuzz payload. This is correct for most web applications, but sometimes you want the raw unencoded character. For example, when fuzzing a non-HTTP protocol or a server that does double decoding, use raw to disable all encoding. Even more powerful, ENC allows per keyword encoders. Example, ENC fuzz URL encode B64 encode will first URL encode the payload, then base64 encode it. You can chain multiple encoders separated by spaces. Encoders include URL encode, B64 encode, base64, MD5, SHA-1, SHA-256, and even double URL encode. You can also apply different encoders to different keywords. This is essential for bypassing WAF rules that look for plain payloads. For instance, a WAF might block or 1 equals sign 1 but not its base 64 version. Encoders are applied in order from left to right. Be careful, encoding changes the payload length, which might affect your matches. Use V to see the actual sent payload. Let's build a real command. FFUF users txt user w10k passwords txt pass https://api.example.com/login x post h content type application/json d username user password. Pass is MR success vertical bar dashboard vertical bar welcome FS89 ACT30 rate 10 O findings.json of JSON. What does this do? It uses two word lists, usernames and passwords. In clusterbomb mode default, it sends post-JSON data. It matches responses containing success, dashboard, or welcome. It filters out any response with size exactly 89 bytes, the generic error pages. Auto calibration removes additional false positives. Concurrency is 30 threads at 10 requests per second to avoid rate limiting. Finally, it saves matches to findings.json. This command could be used to test for weak credentials on an API. Each flag solves a specific problem. MR filters by content, FS removes noise, AC adapts to the target, and rate protects your IP. That's how professionals fuzz layered filtering and save results. Here are 5 common mistakes. 1. Forgetting rate or P on live targets. You'll get banned instantly. Always start with rate 5.2. Using recursion without recursion. Depth a single directory like /static could spawn millions of requests. Set a depth of 2 or 3. 3. Overfiltering with AC. Sometimes the baseline invalid page coincidentally matches a valid page. Run a small test without AC first. 4. Using mode clusterbomb with two 10k word lists. That's 100 million requests. Estimate WCL your word lists. 5. Ignoring ignore body when you only care about status codes. Fetching bodies wastes bandwidth and time. Use ignore body for speed. Best practices. Always use a proxy like burp for the first few requests to see what's being sent. Save results to JSON. Use V initially to verify filters. Respect robots.txt. If you are testing a production site, do it during low traffic hours and have a written authorization. Fuzzing is powerful, but with great power comes great responsibility. We've covered every flag in FFUF v2. 1.0 dev from basic word list to advanced recursion. You now understand how to combine matches and filters to cut through noise, how to control concurrency and rate limiting to stay under the radar, and how to save results in multiple formats. FF is not just a tool, it's a methodology for systematic discovery. Here's your challenge. Set up a local vulnerable machine OWASP juice shop, DVWA, or hack the box. Write a FF command that finds hidden directories, then a second command that fuzzes post parameters for SQL injection, and a third that fuzzes virtual hosts. Try all the modes: sniper, pitchfork, cluster bomb, experiment with AC and ENC, break things safely. Then take that skill to authorize bug bounty programs. Thank you for your attention. Remember, fuzz faster but fuzz responsibly. Any questions? Let's go practice.